Hello, everyone. In this demonstration, I will teach you how to calculate the efficiency of a newly developed primer pair. As we discussed during the lecture on primer efficiency, what you will do in order to calculate a primer efficiency is you will first generate a pooled sample of all your cDNA samples. And subsequently, you will generate a serial dilution of this pooled sample. So you will generate a 1 and 2 dilution, a 1 and 4 dilution, and so on. And you will then perform a qPCR reaction on each of these dilutions. And what you will first do when you obtain the results is you will visually inspect them. So this would mean you will, first of all, check on the melting curve whether for each of the dilutions you obtain only one peak at the same melting temperature, because this will indicate that a specific product has been generated, and that in each of the dilutions this is the same product because it has the same melting temperature. And what you will also visually check is whether the amplification curves for subsequent dilutions are separated by one CQ value, because you expect that if you have half the amount of starting material, which is the case when you dilute the sample twofold, that you will need one additional cycle to reach the same amount of product and hence the same amount of cyber green fluorescence. After visually inspecting the amplification curves and the dissociation curves, you can then export the CQ values from the qPCR software. You will obtain a file such as this Excel file here. So here I obtained CQ values for the different dilutions in the dilution series for 3 primer pairs. One primer pair was developed for the gene SOD1, one primer pair was developed for the gene P53, and the last primer pair was developed for the gene HMBS. And I will now show you how to calculate the primer efficiency based on these CQ values. So I will create a new tab here. I will call it SOD1 because in this tab I will calculate primer efficiency of the primers that were designed for SOD1. So in the first column, I will place the dilutions that I used. The first dilution is, of course, the undiluted sample. So here the value will be 1. The next dilution is the 1 and 2 dilution. So here the value is 1 divided by 2 equals 0.5. Then I have the 1 and 4 dilution, the 1 and 8 dilution, the 1 over 16 dilution, the 1 over 32 dilution, and finally the 1 and 64 dilution. Now what I will do next is I will calculate the logarithm of these dilutions because in a qPCR reaction, we always plot the fluorescence on a logarithmic scale, and hence we also have to take the logarithm of the dilution. So I will just type the formula equals log for logarithm, and then the dilution. And then I will pull this formula down, and I will get these values. Then in the next column, I will place the CQ values, which I will copy from my input sheet. And you will see here that the final CQ value is undetermined. Undetermined means that for this sample, so for the strongest dilution, the 1 in 64 dilution, a CQ value could not be determined within the 40 cycles that the qPCR reaction lasted. So this means that this sample did not reach the fluorescence threshold within 40 cycles. Of course, we cannot use this undetermined value to calculate, so we will just leave it out. What we will then do is we will create a graph. So I will click Insert, and then I will generate this scatter plot, which I will insert here. Then I right-click the plot, I click Select Data, and then I will add, first of all, the x values, and the x values in this case are the logarithm of the dilution. I will not select the last one because for that one we do not have a matching CQ value. And then the y values are the obtained CQ values. And then I press OK. Here I will remove the unnecessary decimal spaces just to make the graph look a bit more neat. As a chart title, I can put the name of the gene that we measured. I will remove these grid lines. And then I will also label the axis. So the y-axis represents the CQ value. And on the x-axis, you can see the logarithm of the dilution. Now, what you can do here to zoom in a little bit on the data points is change the range of the y-axis. So instead of having it starting from 0, you can let it start, for example, from 15. Then you can see that you zoom in a little bit more on the range where the values are located. Then the next thing that you want to do is you'll calculate the slope of the trend line or the standard curve going through these points. To do so, you click one of the points, you click the plus sign here, and you go to trend line, you click the arrow, you go for more options, then it will automatically generate a linear trend line through these points, and you will click display equation on chart and display R squared value on chart. And then you can close the panel regarding the trend line. And then you will already be able to see the slope of the trend line here, because the slope is the value in front of the x. So in this case, the slope of the trend line equals minus 3.1636. So this is one way to calculate the slope, but if you want to have the slope even more accurately, what you could also do is calculate it using a formula. So you can type an equal sign, then you type formula slope in English. And then you first need to select the y values. So these are the CQ values. Then you place a comma, and then you select the logarithms of the different dilutions. You close the brackets and press enter, and then you will see that it also correctly calculates the slope here. Then in order to calculate the primer efficiency, you will use the formula that we've seen during the lecture on primer design. And the formula for the efficiency is 10 to the power minus 1 divided by the slope that you just calculated. And then this entire value you will take and then subtract 1 from it. So you place minus 1 at the back. Then you have the primer efficiency, but generally we like to express it as a percentage. So we will simply multiply this value by 100. And here you can see that the calculated primer efficiency is 107%. This falls within the range between 90 and 110%. So the efficiency of this primer pair is okay. What you will be able to see is that if you remove this minus 1 at the back of this primer efficiency calculation, you will obtain a value that's very close to 2. And this 2 indicates the fact that with this primer pair, the amount of amplicon is doubled in each PCR cycle. So it's doubled, so this means it's amplified by 2, hence the number 2. But as we want to express the values as a percentage, and ideally we see 100% as a perfect result. We use the formula with the -1 added in back to be able to calculate a percentage where 100% is a perfect primer efficiency. So in this way, you calculate the primer efficiency, but then as I mentioned in the lecture on primer efficiency calculations, it's also very important to check the correlation coefficient, or the so-called R-square. And this value should be as high as possible and should definitely be higher than 0.99. You can see here that this is the case. And a high R-square value means that the individual points of the curve here, so the individual dilutions, they all nicely fit onto the trend line. Because you can imagine that you could obtain a trend line with a very similar slope, but where each of the points very strongly deviates from the trend line. So for example, this point might be much higher than the line, the other point might be much lower than the line, and so on. But then still, it would be possible that the trend line would have more or less the same slope, and that accordingly the efficiency would be okay. It would again be close to 100%. However, in that case, it's very likely that something went wrong with generating the dilution series. And even though the efficiency would be considered okay, the result is not really reliable. So therefore, it's very important to always check the R-square value as well. Now, we can easily do the same thing for the other two primer pairs that we generated. So I will just create a copy of this tab. So I do this by right-clicking, then select Move or Copy. Then I select the SOD1 sheet and tick the box next to Create a Copy. Then, as you can see, my tab has been copied, but this time I will rename it to P53. I will also rename the title of my graph to P53. And of course, I will replace the CQ values by those that we obtained for P53. I will paste them here. In this case, I can expand the graph with this extra dilution, because in this case, there was a CQ value determined for the final dilution in the series. And also for the calculations of the slope, we can expand the reach of this calculation and also include the last values. However, what's very clear to see here is that the first dilutions in the series are nicely on top of the trend line, but the last two values in the series are very strongly deviating from the trend line. In this case, it's okay to leave out the last two values from the calculations. Of course, you cannot leave out 5 of the data points, but in this case, it's okay to leave out the last two. So I will do this here. So now you can see if I leave out the last two data points, my R-square increases from 0.8 to 0.99. So the trend line that we generated from these first 5 dilutions is reliable. So then, of course, we also need to calculate the slope only based on the first 5 dilutions. Voila. But even though the correlation coefficient, so the R-square, is okay, you see now that the primer efficiency is too low. So you see that the primer efficiency is only 72%. So this means that the reaction is not optimal and that the amount of PCR product is not doubled in each cycle. However, doubling of the amount of product in each cycle is assumed during the data analysis, and therefore this is not an appropriate primer pair to use. So in this case, I would recommend designing new primers for this specific gene and retesting them. And then finally, I will also copy this tab to calculate the primer efficiency of the last primer pair that we generated. This was a primer pair for HMBS. So I will also change the title of the graph in this step. I will again replace the CQ values. The final dilution has an undetermined CQ value, so we cannot use that. Then we will again select whether the range of the graph is okay, which is the case here. Here you also see that all data points are nicely on the trend line, and we also see that the R-square value is larger than 0.99, so the obtained data are reliable. And in this case, you can see that the efficiency is 104%, so it's also within the range from 90 to 110. So this is also a good primer pair. So this primer pair can be used in the respective experiment. So this was a short demonstration on how to calculate the efficiency of a newly developed primer pair. And you can now use this method to calculate the efficiency of other primer pairs that you have developed or designed and that you want to use in qPCR experiments.